Electricity is one of the most important resources in modern life, yet most people have no idea how it is actually produced. We flip a switch, plug in a device, and expect power to be there instantly. But behind every outlet is a system designed to convert energy from one form into another. The interesting part is that the basic principle behind electricity generation is surprisingly simple. With a few common components and a basic understanding of how energy moves through a system, it is possible to build a small generator at home, not a power plant, not a complicated industrial machine, just a simple system capable of producing useful electricity. In many cases, the total cost of the components can stay around $200 or less. Understanding how this works begins with a simple question: why would someone want a small generator at home in the first place? One reason is reliability. Modern power grids are complex systems. They depend on transmission lines, transformers, substations, and centralized generation facilities. When any part of that network experiences a problem, power outages can occur. Most outages are temporary, but even a short interruption can affect lighting, communication devices, and other important equipment. Small backup generators help reduce this problem. Instead of relying entirely on the main grid, a small generator provides a secondary source of electricity that can operate when needed. Another reason people explore home generators is education. Building a generator is one of the most direct ways to understand how electrical energy is produced. The system converts mechanical motion into electrical current using a principle known as electromagnetic induction. This principle is the foundation of nearly every modern generator. When a conductor moves through a magnetic field, electrons inside the conductor begin to move. That movement creates electrical current. In practical terms, most small generators are built using three basic parts: a magnetic field, a conductor, usually copper wire, and motion that allows one to move relative to the other. When these elements interact, electrical energy appears in the circuit. A typical small generator setup might use a rotating disc or shaft holding several strong magnets. As the magnets spin, they pass close to a coil of copper wire. Each time the magnetic field changes near the coil, it pushes electrons through the wire. The faster the magnetic field changes, the stronger the electrical signal produced in the coil. Many simple generators can be assembled using materials that are easy to find. Copper magnet wire is commonly used for winding coils. Permanent magnets provide the magnetic field. A rotating shaft or disc creates motion. Basic electronic components such as diodes or rectifiers help shape the electrical output so it can be used by small devices or stored in batteries. In a small workshop setup, the coil is usually mounted on a frame so that it remains stationary while the magnets rotate nearby. The coil must be wound carefully so the loops of wire are tight and evenly spaced. This improves the interaction between the magnetic field and the conductor. The magnets are mounted on a rotating surface, often a simple metal or wooden disc connected to a shaft. As the shaft turns, the magnets pass by the coil repeatedly. Each pass produces a small electrical pulse in the wire. These pulses combine to form a usable electrical signal. In many systems, the output is alternating current because the magnetic field direction changes during rotation. If the goal is to charge a battery or power devices that require steady current, a rectifier circuit can convert the alternating signal into direct current. Small bridge rectifiers made from diodes are commonly used for this purpose. The mechanical motion driving the generator can come from several sources. Some systems use a simple hand crank, others use small wind turbines or belt-driven systems connected to motors or engines. The source of the motion is flexible, because the generator only requires rotation to function. Another important part of the design is efficiency. Small generators do not produce large amounts of power, so reducing energy losses becomes important. Keeping magnets close to the coil improves the strength of the magnetic interaction. Using strong neodymium magnets can significantly increase output compared to weaker magnetic materials. The number of turns in the coil also affects performance. More turns usually increase voltage, while the thickness of the wire influences how much current can flow. These design choices allow the system to be adjusted depending on the intended use. A small generator built with inexpensive components will not power an entire house, but it can operate lights, charge batteries, or support small electronic devices, and more importantly, it demonstrates the exact same physical principles used in large power stations. Whether electricity is produced by a massive turbine in a hydroelectric dam or a small rotor on a workbench, the underlying physics is the same. Mechanical motion interacts with magnetic fields. Magnetic fields influence electrons in conductors. Electrical current flows as a result. The real value of building a small generator is Not only the electricity it produces. It is the understanding it provides. Once the process becomes visible, electricity stops feeling mysterious. Instead, it becomes a system that can be studied, improved, and adapted. This perspective is how many early electrical pioneers approached the problem. They started with simple experiments and gradually refined their designs. Over time, those experiments became the foundation of modern electrical infrastructure. A small generator built at home reflects that same learning process. It shows how energy moves through a system and how small design choices affect performance. The key insight is that understanding energy systems often begins with building simple ones. When people interact directly with magnets, coils, and motion, the theory behind electricity becomes much easier to understand. Instead of being abstract, it becomes something tangible. And once that understanding exists, exploring more advanced electrical technologies becomes far easier. If you enjoy learning how practical energy systems work and how small experimental setups can reveal the physics behind modern electricity, consider subscribing to the channel. New videos explore real engineering ideas in clear and simple terms. You can also check the description for a helpful reference that outlines some of the basic components people often use when building small generator systems and similar hands-on energy projects.